Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on July 31st, 2025, so just yesterday. This paper presents the Phi-Ground model family, which sets a new state-of-the-art on several key benchmarks for computer agents. The paper is titled Phi-Ground Tech Report, Advancing Perception and GUI Grounding, and the details of their training process are really insightful. It focuses on a key problem for what are called computer use agents, basically AI assistants that can operate a computer for you. The core challenge is GUI grounding, which is teaching the agent to accurately see and interact with a screen, like clicking the right button. Also, the authors shared their GitHub repository for PhiGround. It's currently the project's homepage, with links to the paper and details on their release plans. They plan to add the model, evaluation code, and benchmark data soon, so it's definitely one to watch for future updates. Alright, so the first figure here really lays out their key results. On the left, we see bar charts comparing PhiGround to other models across 5 benchmarks. In what they call the agent setting, where a specialized model handles the final click, PhiGround achieves state-of-the-art results across the board. Building on that, the chart on the right visualizes efficiency, plotting accuracy against computational cost. This cost is driven by image tokens, which are small pieces of the image the model processes. The red line is the Pareto frontier, showing the best possible trade-off. As you can see, the PhiGround models sit right on that line, proving they're not just accurate, but also highly efficient. To give a bit more context for why these results are so significant, this next figure frames the whole problem. It shows the evolution of agents from traditional limited systems to advanced general ones, both in the physical world and the virtual one. In the virtual world, it contrasts older web app agents, which are stuck using fixed code or APIs, with the goal of a true computer use agent. This is an agent that can perform any task a human can with a computer, which requires something called action grounding, translating a high-level goal into precise mouse and keyboard actions. Now, to teach an agent that kind of complex action grounding, you need an enormous amount of high-quality data. This figure shows the impressive pipeline the authors built to create it. They start with Common Crawl, which is a massive public archive of the web, and filter billions of pages down to a core set. Then, they render these pages into screenshots with different shapes and resolutions. After another round of smart filtering to remove noisy data, they use GPT-4o to label over 10 million interactive elements, creating the rich dataset needed for training. Okay, so besides just scraping the web, the authors also built a complementary dataset using high-resolution screenshots from desktop applications. This table here breaks down how they sourced that data. They focused on 66 popular Windows applications across 6 different domains, including things like Office and productivity, gaming platforms, and even core Windows tools. For each domain, they created specific search queries to pull relevant images using Bing. This targeted data collection ensured their training set included a diverse mix of real-world desktop interfaces, which is crucial for building a more capable and general agent. Building on that idea of diverse data, the authors also dug into the nitty-gritty of the training process itself. This table here explores a fascinating detail, the order of input modalities, which just means the different types of data, in this case, text and images. They tested whether it's better to show the model the image first or the text instruction first. Well, the results are really clear. Feeding the text first provides a significant boost to accuracy across all benchmarks. This simple change makes the model's image processing instruction aware. It knows what to look for before it even sees the screen. And the culmination of all these careful training choices is on full display in this large comparison table. It pits the PhiGround models against other leading approaches across 5 different benchmarks. The results are split into 2 key scenarios: an end-to-end setting, where a single model does everything, and an agent setting where a larger planner model guides a specialized one. In both cases, the PhiGround models, which use a method called direct preference optimization, a type of reinforcement learning, set a new state-of-the-art across the board. So the big takeaway here is just how much the training details matter for building these powerful computer agents. Simple things like input order and the use of reinforcement learning made a huge difference, pushing PhiGround to the top. That's it for this episode of the